there will be a fluid structure interaction. Either it can be one way or it can be two-way interaction. It can be electronics to structures. It can be fluids to electronics. It can be all the physics with the semiconductor like chip packaging where you see your thermal results. You might be seeing your air flows. You might be seeing your stresses because of the thermal effects onto the PCBs and so on. So similarly, you'll be having multiple physics for multiple scenarios because as we know, whatever the product or whatever the scenarios you'll be having, they will be dealing with more than one physics. That's for sure. Right? It's not only isolated for fluid or not isolated only for structure because 90% of the product will be dealing with multiple physics. So multi-physics is the key. If you know many physics or multiple things, it will be easy to understand the problem or get more insight into the problem. So as Ansys, the multi-physics simulation platform, it's a CAD agnostic. That means you can take a CAD from any vendor. It can be a SolidWorks, it can be CATIA, it can be NX, it can be PTC, Inventor, or EPS. Those CADs can be modeled or meshed within the Ansys platform. And we have a different meshing tools. Like as I mentioned, we have fluent mesher, we have SCCFD, we have workbench meshing, we have turbo clip. And there could be a different products or different simulation needs. We cater a different requirement for the meshing. So that's how you can generate a different mesh or different modeling approaches for different physics. For instance, this is a structural for a landing gear. This is the fluid for say landing gear or the this missile dropping. You have the electromagnetic where EMI, antenna, and other densities you can check. You have system level simulations where you can model the system as it is instead of going with a single physics. Or you have the lighting simulations like optical simulations to see the lighting or the other aesthetics performances of your simulation. And at the end, whatever the physics you are dealing with, you want to optimize the things. And that's how the DOE, the design of experience or exploration or the optimization comes into the picture. And at the end, you want to reduce the complexities of your numerical simulations. And that's how the ROM, the reduced order modeling, will come into the picture. And this all set of tools are available into the Ansys, whether it's a technically breadth or depth, if you see. And everything is bundled into the Ansys packages depending on the licensing which you will have. So here is some small list. It's a partial list. It's not the complete list for a particular physics like a fluid, structures, electromagnetics, semiconductors, or software and systems, or optical like the lighting simulation. And there are different set of products which can be help you to perform this type of analysis. So there could be different requirements which will help you to understand different physics, and that's how you might need to use these different tools whenever you are tackling with particular simulation data. So this is one small example in terms of aircraft systems. You can see there are many fields like you have the aerostructure, you have the aerodynamics design, you have the avionics for display, or the flight controls, you have the infotainment systems, environmental controls, a landing gear design, or electronic or electric system design. You have the lightning management or icing effect onto the aircraft or engines, or the propulsion system of the aircraft. So there are many fields, and in each field you have many problems to deal with, and all that things can be catered within an Ansys simulation platform. It's not only limited to these things. Say if you consider the defense, where you can see the advanced material is what you'll be looking at, like what are the stealth design will be saying. There might be issues with if your enemy is going to detect it. So you may want to have the signature and stealth design so that it is kind of invisible for the enemy. It can be an environment where you want to connect with different things like from the ground to the aircraft to the ground and other connectivities and so. You might be having the aerodynamic design of the stuff. You might be having the antenna or sensors designs or their performance checking. Like that, there are many things, store separations and all, which will be dealing with many problems in a hand in particular vertical of industries. And these are very common in all the industries, not only limited to only aerospace or only defense. Similarly, if you see the submarines or onto the ships, there are different types of problems which can be catered within the ANSYS simulation, right? Like the aerodynamic effects of the antenna or integrated propulsion because it's dealing with water, right? And so many other things where you can actually go and have the different tools to assist you to do the virtual prototyping and see the effect how it is going to be performed in that realistic scenario. Similarly, in the automotive industry, you can see there are different physics which can be catered, like batteries. As you know, nowadays we are talking more about the electrification, and that's how the batteries and the performance or the radar, if it is autonomous vehicles, how it is going to perform without a driver. So there are so many things which are going to cater for your simulation needs. So many projects as academia you can take it, and nowadays as we are going with academia industry partnership, it will be very much helpful if you already do this kind of or you handle this kind of problems, so that you will be already aware of what is happening in the industry and how you can contribute from your side. So after this, I'll just run a small video which will give you an idea about the answers. So, right.
Anil, video is not playing the sound. Hello, Anil.
Well, so after this, as you got an idea that there is every aspect of life we are dealing, all the products, they need either one or either simulation need, and that's how Ansys is there in all the fields, whether it is the healthcare, whether it is the academia, whether it is any industry, say aerospace, defense, automotive, FMCG, oil and gas, and so everywhere Ansys is used as a simulation partner for our industry. So just to start with our main agenda where we are dealing with the CAD modeling, Ansys is having two offerings. One is the space direct modeling tool and the other is the design modeling. So the main agenda we are going to discuss is on the space one and not onto the design modeler as the time, considering the time. So the SpaceFrame is a direct modeling tool. As the name suggests, it's a direct modeling capability. So it will not have any history-based modeling. Like if you see the other end, the design model is behind the history. Like whatever the operations of tools which you have performed, that will be kind of one by one recorded in your model. Whereas, whatever the operations we are doing, it will be flexible and fast enough, very easy to do the cleanup of the geometry or perform any operation on your geometry to prepare it for FEA simulations or CFD simulations or lighting simulations. And that's why it is more popular into the industry so that user can, not going to depend on the CAD team to do small changes into the geometry or to perform the geometrical parameterizations and so. So these both the tools are integrated within the Ansys Workbench platform. So you'll have the access with this. And going forward more beyond to the specimen, and both the tools can cater to your multiple needs. So the mainly will go with the specimen as I discussed. So what is the specimen? Well, this is a direct modeling tool, easy to use GUI as well as the tools. It's having very unique capability to create and edit your geometries at the cross-section level. At the same time, it's not a history-based modeling tool. So user preferences with respect to geometry changes are going to be accumulated at any time of point. And at the same time, you can do the conceptual modeling and you have the ability to read any natural CAD files or any native CAD file. Like it can be from Katia, it can be SolidWorks, it can be Easy, Annex, or AutoCAD, or any neutral like the Step, Parasolid, IGS. So many file formats are supported, and all the interfaces are linked within it. So just a quick differentiation between the history-based and direct modeling tool. So as we discussed, there is a no feature tree, so that's why there is no constraint. Similarly, it's very interactive, so it's a fast. It doesn't depend on the history, so that's why if you are going to do hundreds of operations and if you want to go and change the fifth operation, it doesn't need to regenerate all the remaining 90 operations. Right? So that's why it's very fast and it's easy to learn. There are very small number of tools which only user need to understand. It's very easy to use by any engineer. It doesn't require to have the CAD training done beforehand, and it's ideal for any unplanned changes. So, what are the different capabilities apart from the geometry modeling or geometry preparation? So, that is one part of a simulation. At the other end, as we discussed, the specimen can help you to prepare your model for 3D printing or additive manufacturing, where most of the CAD packages are having the broken workflows. Means you cannot work for faceted data or the STL or the scan data in the same platform as you do for the CAD. And that's how you'll get a more, better opportunity to work with the specimen where you can work with mix of data. It can be both STL as well as, the normal CAD data. And user can perform all this, handling of these tools, merging, or doing some performances, or checking the models and preparing it for the further. Like you have a dedicated tool to work with the faceted data, which will be capturing the needs into the additive or to the topology optimization. So you have the different tools into the specimen, which will help you to prepare, find out any faults into the particular data, how to resolve them, and how to get the proper CAD out of that. So it's not only for the 3D printing. The next step is the reverse engineering. You may want to reverse engineering the CAD data, which might be just an topology optimization data, it could be just scan data, or it can be any other faceted data which you just want to make sure that you are going to get a representative CAD out of that. Because most of the time, you might be having the tools which may not be directly going to handle the scan data or the STL data, and you need a kind of CAD data. And that's how you might need to reverse engineering whatever the available scanned or the STL data or the faceted data you have. And that's how it's going to help you. So this is one option into the reverse engineering where you have this faceted data. This is the facet. You can see there is the triangulations onto this body. Right? So this is the kind of scan data. In the healthcare industry, it's very much good practice because you don't get the realistic CAD in the health industry. you most of the times will get the kind of scanned or the faceted data. And then the challenge of doing the further designing or further simulation on such geometry will be very difficult if you don't have the good data, or if something is corrupted, something is not good, smooth, and there are some spikes. So it's always good to reverse engineer it or do some kind of smoothing or shrink wrap here in Spaceline so that your model can be ready to go for the simulation. So it's a very easy and quick. You have the spin surface, you'll be creating some patches, and where the patch is, overlapping to your faceted data, you'll get the CAD within some seconds. But this process is again still a little lengthy because right now I'm just creating this patch, but I might be need to create a different patches to take shape of complete shape of your for this particular geometry. And then sometimes as your geometry is big and complex, it may take little while to start which location you want to start, how you want to patch the next patch, how you want to go and connect that. Instead of that, we have worked with the auto skin option, which is very helpful. If you have a smooth data or if you don't have smooth data, you can prepare that in Spaceline to create its smooth data and then you perform this automatic scanning option. So if you have this smooth data of the facets or the scan data or the still data, you just directly run this tool and it will try to give you similar kind of CAD. There might be chances that some faces might be missing because of some complexities, but you have other tools in the geometry by help of that. You can go and clean up that. You can recreate the patches, you can find the missing areas, you can go and quickly fill that areas and so on. Right? So it's not that difficult, but it is going to save a lot of time if you have the smooth data to generate the CAD out of that. Right? And that can be taken directly back to any simulation where you want to perform the simulation. So for instance, this is one DLR geometry from German Aerospace where they have the robot and this is the leg of the robot where they want to optimize it. So this is, you can see this is a complete solid structure, and if you just remove this unnecessary areas, right, in this and this area, so that you can reduce the weight, and that's how you optimize it for the density. But once you optimize it, you may want to again validate whether it's going to serve whatever the purpose it is made for, whether the stresses or whatever the deformation is going to perform, it is going to experience, whether that is going to be validated with this optimized shape. That's how we'll go for the optimization study. And then you can actually go for quick conversion of this faceted data. Say for instance, this is the faceted data after meshing or after optimization. You can directly go and convert it automatically without merging any faces. Whatever it is, just convert that facets into the surface. So here these strangulated surfaces are nothing but these strangulated facets. Or you can use the auto spin option to get as much as possible as all the CAD faces, which will be most of the algorithms may not read this data, or it may take a longer time to read such data. You might need to do the patch independent meshing and so on. But in these cases, it is a kind of a CAD and it will be easy to read in any other CAD packages or within the Ansys, and we can go ahead for the simulation. Or as a user or as a design engineer, you might need to design it from the scratch. So it's not a kind of reverse engineering, but taking the effect or the references of the optimized part will be redesigning this part from the scratch into the native CAD. So this is how the topology optimization can be done. It can be a direct engineering or it can be a reverse engineering where you'll be using either the spin surfaces or the acid skinning or just converting whatever the faceted data you have into the small triangular face data, surface data. Right? So this topology optimization is used in a different thing, like it can be a validation study, it can be just reverse engineering the CAD or for 3D printing or manufacturing. Right? So in Ansys mechanical, we can, when you are running any topology optimization simulations, you can write the STL data directly from the topology run, and whatever the exporting you are doing, depending on the topology optimization results, whatever you can see into the mechanical window, that can be exported as it is. So if you see, this is a disconnected data. So it is not going to serve your mechanical or whatever the products which you are going to produce. So once you bring this back to the specimen, you can actually go and join this wherever the gaps are there. So this may not be required to perform whatever the design goals of this particular bracket is there. But as a part of production, you might need a continuum data. Right? So you might be going and adding this data, and then you'll be creating another CAD. And that CAD you can again take it for the verification study, so the validation of what optimization shape you got, whether it's going to perform the same job or not. And that's how this testing will be helpful. As we already discussed, you have different tools to cater different needs of faceted data, whether it is corrupted, whether you want to clean it up, whether you want to add or separate it out, you want to smooth it out, or you want to do the shrink wrap to resolve some of the gaps or unknown defects into your channel. And at the end, we'll be doing the subtract and merging between, this is, you can see, this is a CAD geometry, and this is a faceted data. But both can work together where you can subtract the thing and then you can merge it back to get the proper. Because this is the area where it is going to come into the contact with other components into the assembly. And you may want to have this, kind of a proper contact resolution. If you have a little bit here and there at this location, it should be fine because it's not going to interact with any other components. But you don't want to have any approximation in this area where it is going to interact with any other components, right? So that's how you'll be doing the topology optimization, and then you'll be taking it back for the validation studies, and then you'll go ahead with your simulation. As we saw, the specimen can cater with the topology optimization for reverse engineering, for 3D printing, and at the same time geometry preparation for any physics. The next step is specimen can cater for a requirement in hex meshing. So recently we have added on multi-zone meshing method into the specimen. So user can do a quick a hex meshing in specimen itself. Earlier, we used to do that in either Workbench or in ICMC, but now we can do that in Specimen. So generally, this option is now it's for advanced users, not the entry-level users who may not know actually all the background ideas about how to generate the blocks and generate the meshing. So this is actually based onto the block. So you can create the template. Say for instance, you want to mesh this particular object. But at the beginner, you may not able to do this in one go because it looks little complex. It is having some complexity involved. But this is a similar structure, something like this. So as a template, I can initially create a mesh on this smaller box. So I have one box and I have one oriented kind of another box which is attached to this box. So it behaves like a blade. So the blade in reality can be like this. It can be like this, it can be like this. But the shape of the topology is similar. So I can define the mesh in such a way that the number of edges or number of faces which I'm going to associate over here for my template or whatever the part names which I'm going to use for the template, I'll make sure that everything is mapped to this so that whatever the blocks which I'm going to generate for template can go and fit into this to generate the same mesh. So the next time I'll just go and import my new model. I'll import this old mesh and then automatically it will be associated because everything is taken place here as a name or as the number of edges which are going to interact. So number of edges doesn't mean like here I have one, so that means here I should have one. It can be 10 edges because I'm going to match this and this node. And how many edges are there? It doesn't bother how much edges are there in this. So that's how the template modeling is very much, essential in dealing with complex scenarios. And that is very much easy in working with Ansys Specimen or Ansys Workbench. Then you can do the bottom-up approach into the specimen. Like you don't need to create the top-down approach. So whatever the approach you can see, this is a kind of structure of where we'll be going with the bottom up. Means you can just create the block, you just pull the blocks to take the shape of the geometry. And then you'll associate it back to the geometry to get the kind of explanation and complexity. And this is one a small demo I'll show you on additive how you can you know.
Anil lost the audio. There's no audio in the video.
Now it's there.
No, Anil, we cannot hear the videos. Even last video we lost the sound. We
Oh,
can hear you, but the audio is not playing with the video.
System audio kept on. Unshare and reshare the video. Then system audio should be kept on. Then only it will play.
yeah, yeah, yeah. I think system audio is there. Let me see. Now it's audio.
When you share it in the top, there will be an icon for audio. You should click that icon.
Sorry.
When you share the presentation, you will in the top there will be an audio icon, system audio. So you should click that icon so that audio will be played.
This one only, right?
Can you play? We will check. Can you play this again? We cannot hear anything.
Nothing.
Okay. Fine then. Then I'll just wait with this. Fine. Anyhow, the audio is there. So shall I run because I'm able to hear. Not sure if the recording will help.
Maybe you can share the. You can explain the video. And
Yeah,
Yeah.
I think that way I can.
Maybe you can walk through the video as it plays.
Sure. I'll do that. Well, so this video will talk about how you can prepare your model for 3D printing. So here you can see you have 3D geometries as well as surface and data where you can do different merging subtract operations. If there is some corruption, you can go and do automatic fixing. You can see it's trying to do all the automatically. We can add the surfaces, we can create the geometry, we can fill, and at the end we can merge them together to get the final option. So this is a merging of a solids as well as the CAD. This is you can see the 3D printing or the optimization. So you want to resolve the solids or volume inside. You can do the shelling, wherein you can go and remove the internal materials. You can see how it's. Shelling can go for different shapes of different internal structures. For instance, you can see there will be a different structures. You want to take the sketches, you can recreate the CAD, and the sketches can be created as a reference geometry from where you can just take the common edges and then just go back to the sketch and recreate it. So it is a very easy to actually deal with this kind of operations in this case. If you are working with very large or complex material or data, you can see there will be a separate geometry, and you may want to separate it all. So you can see your geometry is having all different components, so they are not a single component. For instance, you want to work with external aerodynamics of this, you may want to have a kind of a single data. You can see it's a separated data. For printing also it will be easy. If you want to again personate everything, you can go and you can do the Boolean operations. This is the geometry modification onto the HTML data where we can recreate and again you can merge it back as per the requirements. So you can see here it's a merging of solids as well as the HTML data to get the final geometry. This is how different things can be done in the space plane, like analyzing, printing, simulation, or repairing, manufacturing. Thanks so much. Fine. So up to this section, we have seen about modeling, geometry modeling tools, or how you can prepare the models for either CFD or either FEA or either 3D printing or optimization and so on. Now we'll go to the meshing tools. As in the initial slide we discussed, we have different meshing tools to cater different requirements of the industry. Like some industry or some industrial problems like chemical mixing or external aero, high speed flows and so, you might need to deal with the hexaheader meshing. Some other complex problems like automatic HVAC system or underwood thermal management or some other oil and gas offshore models, it may require to deal with a very large data and your mesh will be in 100 million, 200 million and so. So dealing with such large data, it will be difficult in one tool, but it will be very easy in the other tool. So that's how we have a different tools for capturing the different requirements of the industry or the user, and everything is bundled into the same key. So if you have the access to this workbench machine, that means you have access to Fluent machine, you have access to IPN, you have access to Turbo, right? Because this is a single tool which can work differently as a different UI. So in Ansys machine, we have a workbench machine, which is a general purpose machine tool, and mostly it is used for the multi-physics requirements in the workbench. The second tool is a Fluent machine, which is mostly used for any CFD applications where we are dealing with very large and complex geometry, and the mesh count may be very high, like in millions, like 100 million, 200 million, and so on. And you have different algorithms to build or handle this machine with the parallel processing available into the Fluent machine. It is very much possible to do the scripting or journaling for Fluent machine so that you can automate your procedures or whatever the workflow which you are going to follow. Similarly, there is another tool called ICM-CFD which will be used mainly for generating hexamation, which is a good quality hexamation tool called as a blocking. And this is also scriptable. And this can be used for both CFD as well as for mechanical or the structural needs. There is one very niche tool for CFD applications within only a turbo machinery where you want to generate automatic hex meshing. So for turbo machinery applications, the turbo grid is very much useful. So there are set of tools which will be used for automatic mesh generation for hexaheader. So the CFD is nothing but your computational fluid dynamics. FEA is your finite element analysis. And similarly, you have the tools to cater all these things. There is electromagnetic analysis also for motors, generators, as well as doing the EMI, SI, AI, and all. So there are separate set of tools that can be used in electromagnetic industry. So that is also available in Ansys. Okay. Fine. So as the focus of this, we'll be checking what is the Fluent machine, how it can be used, what are the different benefits of Fluent machine when you're working, what are the benefits of workbench machine and ICM-CFD. So at the end, all these three tools can be interacted. Means you can take you can generate the mesh here, you can take it to fluent meshing, or you can generate in workbench, you can take to fluent meshing, you can generate mesh here, you can take it to the fluent solver for CFD, you can take it to the mechanical solver, and so on. So only thing or the differences here is that depending on the industry, like you might need to, like as I mentioned, you have the 100 million mesh or 200 million mesh. If it is just a tetra and prism, it is an unstructured format. What if you want to generate the hexa meshing to reduce the total mesh count? Or what if you want to generate the polyhedral cells or polyhexagonal meshing or cut cell meshing to reduce the mesh count? So that's how the requirement in terms whether you want to use the workbench meshing for that particular problem or whether you want to use the fluent mesher or ICMCFD. So you have all the licenses with you, you have all the tools with you. It depends on which problem you are going to solve, which hardware you have, and which particular method is going to give you the benefit for your simulation. Right? So currently for most of the CFD applications, we are using the fluent meshing. If there is any specific requirement of only hexahedral meshing, like as I mentioned for high-speed flows like Mach 5, 10, or the re-entries of vehicles where we want a completely hex mesh, we can go with ICMCFD. Or if it is a multi-phase scenarios where you are doing the coupling with, say, from mechanical to fluent, you are transferring the, the mechanical deviated shape to finally count how the fluid volume is going to generate, or from fluent, how much temperature or how much pressure is going to insert on your mechanical boundaries. You want to couple it back to the mechanical. So such kind of problems can be solved. We call it as a field structure interaction or any other coupling like thermal, electrical, or electrical and fluids. So all that things can be catered to the workbench. Right? So this all depends on which particular industry or which particular simulation which we are going to work on. Then fluent machine in more depth it will go. This is a very advanced CFD machine tool where a lot of different algorithms are available to handle complex geometry and to handle million or billion of mesh. So you can generate a mesh for very large or complex or even the dirty CAD. So there is a separate workflow which are defined into the fluent machine. So the beginners can also easily go through with this. So there are tailor-made workflows. You don't need to just say, okay, this is my geometry, this is my local sizing I want to apply on this particular location. This is how it is whether solid or this is the fluid region or if this is the void region. How many prism layers I want to generate the mesh into the volume and then generate the mesh. That's it. It's so simple to use. Right? Similarly, you have the workbench meshing as I told, it is for your multi-phase cases, where you will be dealing a mix of elements like it can be hexahedral, it can be tetra plus hexa, it can be only tetra prism, or it can be only hexa. So like that different products may have a different requirements like it's, within FEA, it can be a non-linear problems, it can be linear, it can be acoustic problem, it can be the multi-body dynamics and so. So many things can be catered into the workbench measure. Right? So and at the same time we can take these measures to CFD applications if you are dealing with the CFD with the moderate geometries. It is very good tool for doing the parametric study. So if you have the parameters, you can import the parameters from native CAD or you can create them in a space plane and you can deal with the parametric studies to see what is the optimized results you can get. And then finally the ICM CFD, which is again the interactive mesh editing options available, which is there in a fluent meshing. So that user can do the bottom-up approach, user can do the first surface meshing, it can improve, then it can be filled with the volume meshing. So there are different algorithms, but currently this particular meshing method will be used only to deal with the hexa meshing. Okay. So after looking into these three methods, ICMCF, workbench meshing, and fluent meshing, we'll go in little more details about the fluent meshing. So in a fluent meshing, as I told, it can cater like you can take the surface meshes from any or different tools. It can generate from ICM CFD, it can be generated from workbench meshing, it can be generated from any other third party tools like Hypermesh or Ansys and so on. And then you can import that to the fluent meshing. You can remesh if required, you can retone it, you can improve the surface mesh, and then you can fill with the point. Or if you have directly the scan data or STL data or the CAD data, we can directly import that. If it is a very dirty model, like in automotive industry, it's a very common practice. They will have very dirty models like for under thermal management or complete external data, because if you see the automotive CAD, it's not one person is going to design the complete geometry for your car, right? There will be separate team who will be only working with engine. There will be separate team who will be only working for the exteriors. There is only separate team who will be working for powertrain and some HVAC systems like your compressors and so on, right? So there are different teams working different, and then finally everything is going to club together to form a single CAD. So there are chances that there is a mismatch of the data. There are some loose data. Instead of coming as solid, it may come as a surfaces and so. So it's very easy to handle such a dirty, CAD data into the fluent meshing, and you can generate the mesh, very good quality mesh. And then depending on which particular algorithm you want to fill, you have the options to generate the tetra mesh, a hex core mesh, a polyhedra mesh, a polyhex core mesh, and cut cell mesh. And then you finally take it to the solver, which can be a Fluent or any other solver which can handle this type of mesh. So, as I mentioned, the Fluent is there to help you to solve all the CFD, computational fluid dynamics problems. So, wherever there is a fluid dynamics, you can think of as a Fluent. Whether it is the external arrow, where you want to find out the lift and drag, whether it is resolving your complex pressure drop across a heat exchanger, whether it is a chemical industry where you want to see the mixing, whether it is a gas turbine engine, whether you want to do the EMI and all, like electromagnetic antenna, where you want to see the wind loading and all, or it can be any other physics reactions or combustions or any other thing. You can have the Fluent as a solver, and at the same time you can use the Fluent meshing to generate your mesh and specify to prepare your geometry. Right? So most of the times we'll be dealing with repetitive geometries or repetitive tasks. So you don't want to waste much time to do again from the scratch. You know that it is going to be a repetitive work. You can actually create the scripts. You can actually create the journal to automate the process. And that's so it's very easy to handle that in a. So the strategy in coming days for Fluent is to have the simplified and streamlined end-to-end workflow, where you start from the geometry till the post-processing. Everything can be catered into the single platform, right? So these new workflows have developed to cater all these requirements. At the same time, it's much robust and much more user-friendly, right? It's more faster and more accurate than any other tools to capture the geometry as we discussed. So whatever the simulation you are going to do at the end, it definitely have the effect of how it's going to be captured, how you have modeled the geometry, how you have got the mesh, whether it's able to capture all the physics or whether it is going to capture all the features of your geometry, where you are have, say, for instance, your geometry is having this small gap or proximity area. If the flow is going fast with a fast speed from here, whether you have a sufficient number of elements or nodes to capture that physics, whether you have the number of prism layers to capture the boundary layer phenomenon you have all, and so on. So there are different things needs to be decided before you go for any application or any simulation. So for PFD meshing strategy, as we discussed, Fluent meshing is what going to be used for all the needs of your CFD applications. as it is having the parallel meshing capability, so it's very fast in terms of generating the mesh. So within a minute, you can generate 2 to 3 millions of mesh, like that speeds are there, if it's completely polyhex core meshing. Similarly, you have this mosaic-enabled meshing from the recent version, which will be going to help you to reduce the total mesh count. So earlier, suppose for instance, this is a cyclist external arrow, where you want to see the drag on this. So it might be generating, say, hundreds of million of mesh with just tetra and prism. But once you switch it to the hex poly, which is called as a mosaic meshing, it can be just a 20 to 30 million mesh count. You can save that much of mesh count, and that's how your total simulation time can be also reduced. Right? At the same time, we discussed that you might be having a very niche requirement to work with the turbomachinery application. In that case, you can use the turbo grid to generate the automatic hybrid or automatic hex mesh. And if you require to have a complete hexahedral mesh, you can go with ICM. So if you are a CFD user, if you are doing a hexa meshing, think of ICM. If you are dealing with any turbomachinery applications like bladed components and so, you can think of a turbo grid, which is automatic meshing. And rest of other applications which you are dealing with the CFD, you think of plain meshing. So the 90% of the time you will be using this, and the remaining 10% you will be using this. So this is a new workflow where you have the watertight as well as the fault tolerant. So if your geometry is watertight, means there are no flaws in geometry, it's properly connected, everything is enclosed, you have the solids. So you can go with this watertight geometry action. If your geometry is like this, you want to do the underhood management, thermal management, or you want to do the external flow plus underhood thermal management, then you may not waste your time to clean up a lot of things. Instead, you go with the fault tolerant meshing, which can be used to handle such dirty geometry. Even thousands of parts can be easily managed and easily meshed. Right? So the new Fluent experience, how it is there, you can see you can work with the geometries. You can once take the geometry to the plane meshing, you can generate the surface mesh over it. And you have the workflow defined, like importing geometry, then creating, giving the local sizing, and creating the surface mesh. Then you will be saying whether you will be only working with the fluid domain, or it's both, like conjugate heat transfer. You might want to do PHT analysis where you want to deal with both solids as well as fluids. Then you can consider both solids or fluids. So you have to actually tell whether you are going to consider both or it's just a fluid domain. So if it is only fluid, it will be only meshed of only for the fluid domain. But you have the both, it will be meshing both the regions, solids as well as the fluids. And at the end, you can see the volume mesh with the required qualities or required prism layers. This is a polyhex core mesh for this information. And then you can similarly set up and solve your problem into the same environment, because Fluent comes with both either the meshing or either the solver mode. So you just need to click onto the switch to solution mode. Once the mesh is ready, you just need to click onto the switch to solution mode, and then it will go to the solver mode, where you can set up your problem, you can solve it, and then you can do the post-processing. So that's how it's so simple. You can just simply use it from scratch, like from geometry to the post-processing in a single workflow. So this is the task-based workflow as discussed. It's more tailored, so user will have access what to do, and everything will be automatically actioned. So you can go actually and use geometry info, local mesh sizing, generating the surface mesh, improving the surface mesh, and so on. And then finally, you can write this mesh, go to the solver directly from here. So this is a very fast comparing to the older methods or older approaches, and hands-on time is very less. So user just need to follow this step. So that's how there are less clicks. You just need to guide how it's going to import the geometry, how it's going to give the local size, how means different parts are there, like whether it's a skewed or solids, what are the walls, what is inlets, what's outlets, symmetries, and so. And then just finally generate the volume mesh. Like you have the option to give the regions and so. And then finally you'll get the mesh. So if this mesh, you can see this is the geometry and where you generated the polyhedra mesh, right? So you will have actually all the mesh getting generated with what are the controls you have given. And it's very fast because of the parallel processing. So you can use by default 4 cores, but if you have many cores, you can utilize for the meshing on your, I mean, it requires the physical core. It's separate than your HPC pack. So for solver, you might be using the HPC, but for meshing or other requirements, you have to use the local physical processors, of course, available on your system. This is a Formula Student 1 task, which is around 70 million mesh count generated within 1 hour. This is the automotive battery assembly. As you can see, the batteries are very thin. You have the different pack of batteries and they are very thin model. And if you are going to do the thermal analysis or CHT analysis, you might need at least 2 or 3 cells through these small gaps. And if you are going with the tetra or the other mesh approaches, the total mesh count for this geometry may be in hundreds of millions. But if you are going with the polyhedra mesh, it can save your mesh count like drastically. It can be within 20 million or 20 to 25 million. So much difference you can get it with different meshing algorithms, and this will be very helpful to capture all your thermal properties or temperature profiles on your geometry. This is the external airflow where you can see the mesh of polyhex core. So you have the polysurface mesh, you have the polyhedra prism, you have the polyhedra transition elements between the prism and the hex core. So you are not considered the poly into the volume because you can save further elements if you are going with a successful kind of approach. So you can see there is a transition. So from smaller size to the bigger, to the bigger, to the bigger. So you see if there is not much physics going to happen in this particular area, you can have a little coarse mesh. But when it comes near to the bodies or to the surfaces, you may want to have the refinement. You can see the refinement is there to capture the engine weight. Similarly, you'll be having the refinement to capture your aircraft weight or the wing weight and so on. So like that, we can actually define the density region. We can define where we want the density of the mesh and where you want a kind of coarse mesh where you can save the mesh count. And that everything is very easy to handle into a measure. So as I told, the accuracy and the solution time depends on which particular algorithm I am choosing, right? So if I am choosing this tetra and prism, I may end up with 60, 70 million mesh count. I may end up with a similar kind of result, or results may be little off from the requirement. But if I go with the poly or polyhex core, I may just generate the mesh of 20 million, the same mesh for this model, and at the same time I'll get better results with the less time for solver, because solver has to just go with the 20 million cells, which it has to go with 60 to 80 million. Right? So it depends on which particular algorithms we are going to use, how it is going to capture your geometry, whether you have captured the properly the prism layer requirement to capture the boundary layer phenomena near walls, and the density like the weight region or where the shocks are coming, whether you have the proper density to capture such phenomena. Right? So that's how all the strategies of the meshing or the geometry modeling affect your simulation. Right? Say for instance, you are doing this external as well as you are interested to see how much the flow is going, what is the pressure drop across the engine. You cannot block it. You should allow the flow to go through the engine. So that strategy we have to do while modeling the geometry or while considering the volumes. So that's how we can actually do the thing while working with CFD as well as working with FEA or while working with any other physics. So this is all related to the CFD. The next is the workbench meshing, which mostly deals with the multi-physics scenario or simulations, right? Where you have the different kind of mesh algorithms. Like you can generate a multi-zone hexa mesh, you can generate the tetra plus prism mesh, or you can have floor tetra. Because if you deal with the FEA analysis, the structural part of analysis, you may not be interested to generate the prisms most of the time, right? So it will be kind of either hex mesh or either the tetra mesh. So in such scenarios, we can use the workbench meshing, and the mechanical meshing is also part of this, where you can easily generate the mesh and then you can go ahead for a simulation for the mechanical. So within mechanical, you can cater many physics. It can be a normal static structural, it can be thermal, it can be acoustic, it can be multi-body dynamics, it can be different composite modeling and so on. So you have a different algorithms to cater the 3D geometry or 2D geometry. So it can, as I told, it's multi-physics meshing tool. So you can generate the mesh for CFD. It can be generated for the FE application. Okay. You have the pixel algorithms also available within the this meshing tool. So if you want to use, you can use it here. But as I discussed, it's always good that you use the fluent meshing for CFD requirements and for catering with the different composite geometry. And you have a different meshing definitions into the workbench, like you can give the global size, like what is the minimum size you want to start with, what is the max size you want to reach, what is the curvature you want to capture, the curvature size is, right? How you want to capture the proximity region, how many cells you want within the proximity region, how you want to have the prism layers, whether you want 2 layers, 3 layers, if it is a CFD problem, whether it is dealing with the Y plus requirement, then how the coastal height you want to give for your prism settings and so on. So that kind of all the requirements are there, whether it's a fluent machine or whether it's a workbench machine, and that can be available here. Sometimes your geometry cleanup or your geometry, modeling will be in such a way that you might be having very sharp angle, or you might have end up with very small faces or small edges, right? Or it can be having issues with some surface topology. So in such cases, you can use the virtual topologies in the workbench instead of going back to the CAD. We can try to do virtually mapping of a CAD over here, so that we can actually get the virtually bigger picture. The smaller edges will be converted to the bigger edges, smaller faces will be converted to the bigger faces. We can use the defiltering tolerances to resolve such complex angles. You can see this is a very sharp angle, but you say, okay, I don't want to capture anything in this region within 5 millimeter area, within 1 millimeter area. Then it will just simply go and patch independently, automatically will try to defeature that feature. Right? So similarly, you can actually see the local qualities by plotting with the different colors to see where the bad quality, where the good qualities, and so on. Then when it comes to the FEA specific applications, most of the user might be working with the shell sampling just to reduce the problem size, right? As you know that you can convert your 3D geometries to either shells or bins. Like if you are working with say cables, you are working with thin sheets like automotive thin sheets or aircraft, exterior, automotive exterior, or this sheet exteriors and all. So you see the other two dimensions are very large comparing to the thickness. So in such a scenarios, if your thickness to the other two dimension ratio is more than 150 or 120, you can use the mill surfacing or the shell approach. Similarly, if you have one dimension which is very long compared to other two dimensions, you can go with the beam approach, right? Because if you are just like as in the previous thing we discussed, if you want to model the smaller thickness, you may want to have at least 2 or 3 cells through thickness. And that will be very huge in terms of capturing the geometry, and mesh count will drastically improve. But in such cases, like in CFD we discussed, I have not told anything in lakhs. I was speaking in the millions. Right? Let's say in 50 million, 80 million, 100 million, 200 million, and so on. So in CFD, it's a practice. You have the mesh in millions. But once it comes to the mechanical or structural, you try to reduce the mesh count. If you have the millions of mesh, that means it's a very huge model. Because if you see the 6 degrees of freedom, 1 million will automatically turn to the 6 millions of nodes where your matrix equations are going to be solved. So that's how you want to reduce the mesh count, and that's how the batch connection are used to reduce the mesh timing. So for instance, if this is the ship model and everything is the shell model, means mid surface, it might be having a hundreds of parts, and to join the mesh, because at the end you cannot just take the separate surface and mesh it, which will be very easy, right? But the end, how the mesh is connected. If it is not connected, you have to define some contact regions in mechanical to solve your problem, right? Otherwise, suppose this part and this part is not connected, and if I'm applying some boundary conditions, I applied some load here, 100 Newton, simply this portion will only fly away. This will be here only. So the effect of load, whatever I am applying here, will not be transferred to all the things which are not connected. So that's how at the end it's required to either define the contact region, to say whether it's the bonded connected, like you might be having the scenarios where it is just a frictionless contact, or it will be a frictional contact, right? So it depends on how the geometries are connected in the realistic scenarios, and that's how you are going to give the thing. So if you see the shape, all these things will be either riveted or all these things will be connected together, right? There is nothing separate, or there is no hinge here. So that means it should be either bonded contact or it should be node to node connected, and that all things will be taken care in the batch setting. In the background, you will be telling, okay, I have the geometry, I want to mesh with this particular size, I want to connect them within this tolerance. So suppose between this space and this space, I might be having some tolerance offset. So that can be automatically taken care if I am taking this tolerance. I can use the multiple tolerance, and I can choose the multiple set of mesh. Like I have one tolerance to go with meshing for this. I can have one for this, or I can have one for this. So it depends on different locations, which tolerances are going to be used, which mesh size is going to be used, and how the connections are going to happen. So that at the end, you'll get the different mesh which is connected. So if you see, this is the CAD geometry, a simple CAD. You have one bottom plate, and you have top 1, 2, 3, 4, 5, 6, 7, 8, a small plate. So you have some gaps between these plates in this direction. You have the gaps in this direction vertically also. And then at the end, you want to connect. So you can see if your tolerances are not good, in the bottom you have these two. Suppose I'm going with the one single tolerance, say 1.2. The tolerance between these are say 1 mm. But tolerance between this side is also between this place is 1 mm. But I'm going with a bigger tolerance, 1.2 mm, and if I say all to all, you may get a corrupted mesh at this, because it says these two things are also in the same tolerance range, so it will try to connect them. It is not the required. So that's how you need to have the separate connection tolerances and the separate set of grouping. So I'll say only these things I want to model with a 0.2 tolerance, so that it will be retained as it is. Then I will say, I want to only model this with this with this, and so. So the bigger tolerances can be given to different groups, and there will not be any issue. But if it is come to the global tolerances, we have to see what is the minimum, what is the maximum, how it is going to affect. But at the end, it's blazingly fast. So you can see this model, which is having around 2,700 different parts, like beams as well as the shell. So the top thing is the beam, and these are all the shells. It just takes 33 seconds to generate the mesh and get the proper connectivity. You imagine 33 seconds. If you have to do this manually, it will take more time than that to just connect it, okay, at a couple of locations. But to handle such big data, it's very smart and fast in the mechanical. Similarly, you can see This is a 836 part. You have all the pins, you have the shells, and you can see at the end how the mesh is connected. So the pink lines is nothing but you have the connected mesh at the face to face. These are the beams, so they are just separated, so they are just a red color. But if they are connected at any junction, it will be a pink junction. Right? So this just took 1.5 minutes to generate the mesh of around 4 lakh elements with 0.4 quality. So here you can see the face-to-face connection with a different color code. If you have the yellow color, that means you have more than 3 faces at the same location. So like that, there are different models which were tested around 800 to 15,000 parts. Say this is a sheep model which was having 15,000 of parts. It took 30 minutes to arrange the shells. Like you have to extract the bits of it, because as a CAD, you will get a different CAD from the CAD designer. It will not be a shell. As a user, you have to extract the shell. You have to extract the pins, and then at the final, you will get a number of parts which can be meshed with this particular algorithm, and that will be much faster to generate the mesh. Then at the same time, as we already discussed this in a specimen to create the template. So similarly, we can create the templates into Workbench. So why Workbench? Because we discussed that Workbench is very good tool while you are dealing with a parametric study. So you are going to model something like this, but at the initial stage, it is going to be very complex to model everything as it is. But the next time this internal structure, suppose you want to optimize this middle junction of tube, you don't know how the internal shape is going to be, but at the end it is going to be a 3-section, tubular kind of pipe. So as a template model, I'll do the simplified model. I'll give the same name selection. So this is a realistic geometry which is having the same names, where inlet is there, where walls are there, where outlets are there, and so. Similarly, I'll model into the sample thing. Then I will first run my sample model with the required boundary condition. I'll take it, I'll open it into the workbench, I will mesh it, I will solve it by giving whatever the required boundary conditions I have. Say mass flow inlet, velocity inlet I will give, pressure outlet I will give, and I'll monitor what are the results I want for a simple problem. And the next step, I'll just go to the template and I'll just replace this with the actual part. So the next time, everything will be automatically carried forward because everything is defined with the same topology, with the same name, and it will automatically understand where it has to go and give the inlet boundary condition, where it has to go and give the outlet boundary condition, where it has to monitor its flows and other monitor controls, right? So everything is ready for you. So you don't need to work onto the complex model itself at the beginning, but you can start with the templates if you are going to do the repetitive studies of some of the components of parts. Right? So this is all related to the workbench. And then last but not the least is on ICM CFD, which I'll cover in 5 minutes. So as we discussed, this is more interactive meshing, and mostly it will be used to generate the mesh for hexahedral requirement of your simulation. Right? So you can even take different types of file format as we discussed. So whatever you import in a space plane, whether it is a CATIA, whether it is SolidWorks, or any other CAD file like SPACE, IGS, Parasolid, same thing, it can be transferred from specimen to ICM, or it can be directly imported into the ICM CFD. Okay, it can be generated with other approaches, like you can have the mesh for hexacore, or you can have the mesh like wrapper, shrink wrap, or you can have the tetra plus prism. So different algorithms are also available. But as discussed, you use this algorithm only in case there is a hexahedral meshing requirement, or else fluent meshing is good enough to tackle all your CFD problems with the less mesh count with the polyhex core or polyhedral, right? Then as discussed, you can use the external arrow, you can use the turbomachinery application, or any structural application, okay, or this is the internal in-cylinder flow analysis, where there is a requirement, like for instance, we say the other mixing location where you might want to have the hexahedral meshing, okay, or you are working with missiles and so you might be generating the hexahedral meshing for such a application, and you'll be generating the mesh in Ansys CFD, which can be taken to either Ansys CFX or Ansys Fluent for further simulation requirements. Then there are different advanced controls actually to capture the mesh. So generally, as this is a block approach, so it depends on how the blocks are going to capture your geometry. So you have the different options to create O grid, L grid, C grid, and so it depends on the shape. So if you have a complete cylindrical shape, you can go with complete O grid. If you have something like a wing only, so it will be a C shape. Right? If you have something which is a quarter like this, it will be a L shape. So your O grid will be L type. Here it will be C type. Here, if suppose you are dealing with the symmetry, it will be again a C type block. If it is a complete aircraft, it will be a O grid, okay, which is going throughout to the fuselage of the aircraft and so on. So like that, there could be a different strategies to generate the mesh and to get the proper mesh with the required white cross. So you can go to e raised to power -6, -7, and so for very fine purpose requirement of high-speed flows of aerospace industry. Right? And that's how it's very much easy to do that kind of meshing in ICM CFD, and you can take it to the simulation. So your total mesh count will be also reduced. At the same time, you'll get more accurate results because of most of the cells are either aligned to your flow or normal to the boundary. Similarly, you can go to the structural analysis, where you can again use the different algorithms like quad or PEV, and you have the different stamping, or you can use the washer treatment and so to generate the mesh. And this is also automatic multi-zone approach to, you just need to give the surface and it will try to create the a quad dominant mesh onto that surface. You have the new advanced controls to improve the mesh. So automatic algorithms are there to smooth the mesh. So initial quality may be less than 1 in this area, but once you smooth it, the less than 1 areas are very less comparing to this area, where you can see more mesh in the less than areas which is quality is very low. And at the end, as we discussed, with a single license, you can use either parent machine, you can use a turbo grid, ICN CFD, or workbench machine. So this ICN CFD is a part of your workbench. So once you install the workbench, you just need to check that ICN CFD also is there while installation, and then it will be installed. So you can actually take the geometries, like you say you are going to work with hybrid, with interface definition, or it can be say MRF zone, like multiple reference frames, where you have one rotating fluid, you have one stationary fluid. So you can model one rotating, one stationary, take both into the solver and have the interface defined over there. So you have this MRF, so you have this fan over here, which is going to be rotating fluid, and the remaining fluid is kind of a stationary, and the effect of both can be modeled into the unified approach into the solver. So this is very much easy to do it in a specified to a plane measure or specified to workbench measure, but the similar thing is also possible with the SNC only. Okay. So fine. So this is all related to all the products which we are going to discuss. After that, I'll just go through 4 or 5 different CFD cases, because as you see, for FEA, the mesh requirement will not be that much complex as compared to the CFD analysis. So there are different classes, like depending on what type of geometry you have. If your geometry is having a lot of corruptions, like as we discussed, you have the underwood thermal management automotive geometry, which might be the problem of class 1. Or your geometry is say helicopter geometry with all the engine compartments, or the aerospace geometry which is having all the engine components and so on. Then how many bodies are there in your geometry and what is the requirement? So depending on, there are different classes. So customer requirement is to generate a complete hex mesh with some editing capability. User can think of ICNC every day. But in these cases, your corruption should be minimum. And you can see either your corruption is high or very high. We generally recommend to use the fluent meshing where we have the fault tolerant meshing workflow, which can be used for that geometry. And this is a very good practice in all the industries, automotive. So you name it, they use this algorithm, fluent meshing, to work on their automatic requirement or for say underwood thermal management, external aerodynamics, and so on. They will handle that with our wrapper or fault tolerant machine algorithms for class 1, class 2 problems, where they might be dealing with hundreds to thousand or more than thousands of components. Like you have the engine, you have the other parts, and so it will definitely go more than hundreds of different cell zones. So it is a very tedious task to work with such big components to do the manually cleanup. And that's how we go with the wrapper technology to generate the surface mesh of a good quality. And then we'll fill with the required mesh or polyhex square to reduce the total mesh count, because the domains will be generally very big. If you consider the aircraft geometry, the geometry itself is 70 to 80 meters long. And then you will consider the domain, say 5 to 10 points again to all the sides. So it will be almost 8 to 900 meters big domain. And if you just generate a mesh of 1, so in such a domain, your first height will start with e raised to minus 5 or e raised to minus 6. So you understand from e raised to minus 5, it has to reach to this bigger sizes, how big mesh count we can generate. But you have a different algorithm like hexahedra, you have a polyhex score and all, which will reduce the mesh count so that your computation resource can be easily able to handle such bigger things. So just an example of a safety class 1 case, this is a helicopter engine component, and you can see there are so many wirings or tubes are coming out of this engine, because there are so many controls which are there and so many systems, and you want to do the flow around with this, and at the same time you want to perform the CHT analysis. It's not only the fluid analysis, but it involves the energy equation also. So it is a very huge computationally, simulation problem, but that's all not a manual, because if you have the HPC, if you have the bigger system, you just need to set up and run it. What takes more time or manual efforts in your pre-processing? How to clean up this model? How to generate the mesh? So if you consider your total simulation time, 60 to 70% of your time will be in the pre-processing. The rest 10% time will be in your setting up the problem and running it, and the remaining 20% time will be post-processing. Right? So handling such a complex geometry where you have 2,500 plus bodies, and you might be having some sheet geometry, some solids, there might be leakages or gaps or overlaps into them, or somewhere there might be a missing location and the domain is not defined. So it's a very huge task for a pre-processing engineer to do. But it's very easy if you have the specimen and fluent meshing. You just take this CAD to the specimen, work on to remove some of the complex region, to find out if there are missing traces, just patch them, find the overlap, find the common junctions, and clean the model roughly. Don't clean completely. It may take 1 to 1.5 days to do the complete geometry preparation. That means you are not resolving any overlaps. You are not going to resolve any, the sheet to solid connections and all. You just only need to find out if there is no leakage, if there is no missing surfaces, if there is no bad patches and so on. Right? But since you have 2,000 plus bodies, it takes a time to cross-check each and everything. That's how the time will go. Otherwise, the actual operation will be late. Similarly, you'll actually go and do some of the meshing iteration, because while working with such a complex geometry, in the first go itself, you may not be going to get the satisfactory surface mesh. So you may want to do 1 or 2 trials to see which sizes are going to be better and which sizes are going to give us the better captured mesh for the geometry. That may go with say 0.5 to 1 day of your time, and then you just create automatic meshing. You can actually have some scripts into the Fluent Mesher. Once you define all the sizes, you can record all the journals, and then you can just run it next time. So first setting, whatever you are doing, you just record that, and next time you know where you are going to change which sizes, you just go and change that sizes and just run it. So within 3 to 5 days, your complete pre-processing can be done for such a complex and rich model. Right? Similarly, for class 2, this is the external aerodynamics model, and this is the scan data, STL data. So to handle STL data, it is again a difficult task if you are not properly getting the model. So again, you have to go back to the faceted data, you have to repair if there are some issues, and so if you see this right bottom image, this is all the faceted data, the triangulations you can see. Right? So this is not the mesh, but this is the data, the CAD model itself, which is the faceted data, which is the STL. So the first thing is what you take it to testline, prepare it properly, create the external domain, and then take it back to the Fluent meshing. But you can see it's just a half-day job. You don't need to do much of things. You just need to find out if everything is in source. Once the domain is created, it will be automatically pulling while doing the mesh into the Fluent meshing. And you can use the proper sizes to define the locations wherever you want to capture the leading edges or trailing edges or any other select areas and all which are your interest. Okay. And there is a third class cases which can be used the workbench. Say for instance, this is the heat exchanger model. So as you know, like in FEA we try to reduce the problem size. So what we did, we saw, okay, there is a thickness is smaller comparing to other two dimensions. We model it as a shell. We saw the third dimension is very low comparing to other two. We model it as a beam. So similarly, this is a CFD problem. We might need to see whether we have to consider this as a complete model. What if we try to reduce the size? What if we can see if there is any symmetry available? What if we have some periodicity in geometry, right? So we can take help of this, whether instead of modeling 360 degree, why can't I model just 45 degree? If it is a linear periodic, why can't I model just only one section that's completely modeling all the things, right? So similarly, all those things, and at the end, you see it's a very thin model. So if you just generate the mesh with a normal approach, it may take a huge mesh count and huge time. But at the same time, you want to parameterize. You may have this curve as a parameter. You may want to change this gap. You may want to change the curvature, or you may want to change this, filtering holes. So these all can be a parametric runs. You can study this to see what you can optimize this heat exchanger for your requirements to see how the thermal effects are going to be improved with the different designs. And that's how we define it as a parametric, a model in any native CAD, and then bring it to the Ansys. Then you do all these mesh setups like global and local mesh sizes, run it to the solver, and then do the optimization automatically. So you have the parametric studies which can be automatically run, and you don't need to do first one set of run you have completed, then the next run it will automatically take care depending on what parametric range we have provided. Only thing user has to take care is that whatever range it is defined, it should be in such a way that it is not going to fail in the geometric creation itself, like the first step. If it is failing to create the geometry, the next steps will not, have any meaning, right? So, but suppose you have hundreds of design parameters, if the 20 number of steps is failing because of some malfunction or because of some parametric range issues, it will still continue with the next, parameter like 21, 22, 23, and so on. And only the 20th range can be separately analyzed. So that way also it is possible with Ansys parametric range, which may not be possible with any other tools. And then fourth one is say workbench meshing again, where you might be having the requirement to have the mixed type of mesh. Like you can have somewhere A tetra mesh, which is the complex region. You may have somewhere the hexa mesh, which is the simple region. And you have the sweepable bodies and all. So which is the complex area? You have the mesh, which is the tetra plus prism, which is a simple area like this, and this, or there is internal. You have the option actually to generate the hexahedral mesh. So you actually have some options to create the worksheets, to create the different name selections, and the name selection can be used to give or define different mesh controls that can be used to define the different boundary condition in your solver. So it's a very user-friendly, very user-intuitive to use the workbench machine for parametric studies or while working with any multi-physics simulations. And finally, the hexahedral requirement of 18 CFD, which is the class 5, where you might be having the geometries for a high-speed aerospace or for any other mixing requirements or reacting tools. Okay, you can go with the hexahedral mesh, and in such cases, you can use license CFD, and you'll be generating. So you can see this is a CAD, and you'll see small lines up there. So these lines are nothing but the blocks which are going to take the shape of your geometry to mesh it. Okay? At the end, the blocks are going to represent your geometry in terms of a mesh, and that is only going to communicate with the solver with whatever the boundary conditions we have defined. Right? So this is all actually from my side. Coming to the design tools which can be used for any physics, whether it's a CFD, FEA, or electromagnetic requirement. You have a space length, you have workbench meshing, you have fluent meshing, and you have IC CFD. So after this, I'll open the floor to question and answers. Before that, Abhimanyu, if you have anything, please.
Thank you, Anil. It was really informative, and just wanted to inform the people because a lot of queries are coming on accessing the recording and PPT of the this presentation, and there were a lot of issues regarding the streaming of the media. For example, video, audio, as well as some people complained that slides are not moving. So the issue could be a bandwidth because it was working well for me too. So we are anyway recording this session. We'll be uploading it at the end of the webinar series on AICTE website, and it will be accessible to all through your contact details if will be shared. So we'll open for polling right now before we move into Q&A, Anil. So maybe we can have a polling session for another 2-3 minutes.
Okay, sure.
Just a second.
Request all to fill the poll and help us on the information.
So I've opened the poll. So I would request everyone to fill in those details in the next 3 minutes, so that we could get the data and we'll be able to reach out to you in case you in case you want Ansys to contact you. Anil, I'll stop the recording here.
Okay.
Then we can go to Q&A.
Yeah.